Ladies and gentlemen, in lesson 7 of group theory, we have covered homomorphisms. Whether it's your first time here or you came back from lesson 7, welcome. In this course, part of what we cover is going to be the proofs of the propositions that we see. In fact, 7.1 will cover the proofs of the propositions that we've seen and a small lemma that we've seen in lesson 7. The first proposition would be a proposition that talks about some of the properties that we've seen about homomorphisms. Following that is going to be a small lemma that relates the injectivity and the kernel of a homomorphism. Lastly, we've seen that there are some necessary conditions that apply when we find out that two groups are isomorphic. And this is all what we're going to be proving in this video. Let's get started. Let us now restate and prove proposition 1. Proposition 1 says that if phi is a homomorphism going from G to H, then phi carries the identity in G to the identity in H. Moreover, phi of the inverse of G is equal to the inverse of phi of G. And lastly, phi of the nth power of G is the nth power of phi of G. This all makes sense because phi is supposed to be a homomorphism, which means that it's supposed to respect the structures of the operations of both groups. Let us now get into the proof. To prove the first part of the proposition, recall that the identity in G can be written as the identity in G times the identity in G. So phi of the identity in G is equal to phi of the identity in G times the identity in G, which, because phi is a homomorphism, we can split up this thing here to have phi of the identity of G times phi of the identity in G. Recall quickly that the operation here is in G while the operation here is in H, because this is inside G and this is inside H. So moreover, we have that this here is equal to that there. We can multiply both sides of the equation by phi inverse of the identity. So we have a multiplication by phi inverse of the identity of what we already have. And recall here that the inverse times itself gives an identity, and the one here is in H equals identity in H times phi of the identity in G. And the identity in H times any element in H gives just the element itself. So we have now proved that the identity is sent to the identity. And the first part of the proof is complete. Next, I will prove that phi of the inverse of G is equal to the inverse of phi G. To do that, I will be using part 1 of the proposition to say that phi carries the identity of G into the identity of H. So recall that by definition of inverses, G times G inverse is equal to the identity in G. So we have that phi of the identity in G, which happens to be the identity in H, is also equal to phi of G times G inverse. And this, because phi again is a homomorphism, we can split up this product into phi of G times phi of the inverse of G. And now we can multiply both sides of the equation by the inverse of phi G. So multiplying by the inverse of phi G, we get this formula now. Here we have that phi inverse of G times the identity is just phi inverse of G. And this is just the identity in H times phi of G inverse, which is equal to phi of G inverse. And thus we have proved that phi carries the inverse of g to the inverse of phi of g, thus proving the second part of the proposition. To prove the last part of the proposition, we will do this by induction. So to do induction, we start with the base case, n is equal to 0. So when n is equal to 0, this means that g to the 0 is equal to the identity in g. And we've already proved in part 1 of the proposition that phi of the identity in g is equal to phi g to the 0, which is equal to the identity in h. So the base case is already proven in part 1. The next case is to prove for n plus 1 when we assume the result is true for n. So the inductive hypothesis tells us that result is true for n, which means that phi of g to the n is equal to phi g to the n. And this we will use to prove the result for the case n plus 1, and thus completing the proof of part 3 of the proposition. So we have that phi of g to the n plus 1 is equal to, by exponent rules, phi of g to the n times g. Using the fact that phi is a homomorphism, we can split this up into phi g to the n times phi of g. And we can use now the inductive hypothesis to say this is equal to phi of g all to the n times phi of g. And we use now the exponent laws to say this is equal to phi of g to the n plus 1, thus completing the proof of the third part and the last in proposition 1. Let us now move into lemma 1, which says that if we have a homomorphism phi going from g to h, then the lemma says that phi is injective if and only if the kernel of phi is equal to just the set containing the identity of g. Let us get into the proof now. To prove lemma 1, we have to prove the statement in both directions. We have to assume now that phi is injective, and we have to prove that the kernel of phi is exactly the set containing the identity in g. So suppose phi is injective. We know already by proposition 1, part A, that phi of the identity in g is equal to the identity in h. So because of the definition of what a kernel is, kernel of phi is a set of all of elements of g such that phi of g is equal to the identity in h. And since we've already found that phi of the identity in g is the identity in h, this means that the identity in g is inside the kernel of phi. Now that we know that the identity is inside the kernel, we have to prove that it is the only element inside the kernel and that there are no other elements inside the kernel. So let g be in the kernel of phi. We want to prove that g can only be equal to the identity in g. So if g is in the kernel of phi, that means that phi of g is equal to the identity in h by definition, but we know that by proposition 1, the identity in h is equal to phi of the identity of g. And because phi is injective and we have that phi of g is equal to phi of the identity of g, this means that necessarily g is equal to the identity of g. This completes the forward direction of the statement of the proposition. To prove the backwards direction, we now suppose that the kernel of phi is equal to the set containing only the identity of G. And now we want to prove that phi is injective. So to prove that is injective, we let G1 and G2 be elements in G such that phi of G1 is equal to phi of G2. We are aiming now to prove that G1 is equal to G2. So we will multiply both sides of the equation by the inverse of phi of G2. So phi of G2 inverse in both sides of the equation gives us on the left hand side this expression, and on the right hand side the identity in H. So phi of G2 inverse phi of G1 is the identity in H. We can now use the third property in proposition 1 we've seen by prop 1 C. We can get the inverse inside the brackets. And now we can use the fact that phi is a homomorphism, and we can combine these two to have phi of G2 inverse G1 is equal to the identity in H. So G2 inverse G1 belongs to the kernel of phi, because phi of that element gives us the identity in H. And because G2 inverse G1 belongs to the kernel of phi, and we have supposed that the kernel of phi contains only the identity in G, this gives us that G2 inverse G1 must be equal to the identity in G. And if you multiply both sides of the equation by G2, we get naturally that G1 is equal to G2, thus proving that because phi of G1 equals phi of G2 implies G1 is equal to G2, that means that phi has to be an injective homomorphism, thus terminating the proof of the proposition. The last proposition to prove in lesson 7.1 is the following. If G is isomorphic to H, then the order of G is equal to the order of H. In other words, the cardinality of G and H are the same, and they have the same number of elements. Secondly, we have that G is abelian or commutative if and only if H is abelian as well. Thirdly, the order of any element in G is equal to the order of the image of this element by phi. Let's get started with the proof. To prove that the cardinalities of G and H are the same, recall that if G is isomorphic to H, then by definition there exists an isomorphism phi from G to H. And because an isomorphism is bijective, that means that the cardinalities of G and H are definitely equal. So the first part of the proof is immediate, since phi is a bijection. The second part of the proof states that G is abelian if and only if H is abelian. To prove that, let H1 and H2 be any two elements in H. Since phi is an isomorphism, then we can say that phi is surjective. In particular, this means that for H1 and H2 there exists some pre-images. So there exists some pre-images G1, G2 in G, such that phi of G1 is equal to H1 and P of G2 is equal to H2. H1, H2 is equal to phi of G1, phi of G2, and because phi is a homomorphism, this is equal to phi of G1, G2, and H2, H1, the same way is equal to phi of G2, phi of G1, and that is equal to phi of G2, G1. So we have that. So if G1, G2 is equal to G2, G1, that means that if G is abelian, so any two elements are commutative, so G1 and G2 is equal to G1, this means that applying phi on both sides of the equation, we have that phi of G1, G2 is equal to phi of G2, G1, and we now know that these two specimens are equal to H1, H2 and H2, H1 respectively. So this means that H1, H2 is equal to H2, H1. So we can now see that if the elements are commutative over here in G, then the elements in H are commutative as well. So G is abelian if and only if H is an abelian, if and only if H is abelian, and we have now terminated the second part of the proposition. To prove the third part of the proposition, we need to have a look at the powers of G and the powers of phi of G. So recall that for all n in n, so for all natural numbers, we have that. So G to the n is equal to the identity in G if and only if phi of G n is equal to phi of the identity in G, because we have just applied phi on both sides of the equation, and that if and only if we use now proposition 1 part C with the powers of n to say that this is if and only if phi of G to the n is equal to phi of the identity of G, and the identity of G is equal to, and phi of the identity of G is equal to the identity of H. So we have that G to the nth power is equal to the identity in G if and only if phi of G to the nth power is equal to the identity in H. So if the n gets us back the identity in G, it also gets us back the identity in H. So in particular, we have that if the order of G is equal to R, this is true if and only if the order of phi of G is equal to R, which means, in conclusion, that the order of G is equal to the order of phi of G. If this was a bit hard to follow, recall that if the order of R is equal, if the order of G is equal to 5, that means G to the 5. So let us say the order of G is equal to 5. This means that G to the 5 is equal to the identity in G. So this is true if and only if phi of G to the 5 is equal to the identity in H, and because the order is the smallest number in which the power of the G to that power is equal to the identity, we know for a fact that G, G squared, G cubed, G to the 4 are all not equal to the identity. But because this is an if and only if, for any number n, we know that phi of G, phi of g squared, phi of g cubed, phi of g to the 4 are also not equal to the identity in H, thereby proving that the order of phi of g has to be equal to 5, and thus terminating the proof of the third part of this proposition, and thus terminating this lesson. If you have liked this lesson, if you enjoyed the proofs of these propositions, please like, subscribe, and share with your friends. Whoever likes group theory, or if they're new to the channel, I strongly recommend you checking out the other lessons, and I will be posting a lot more future lessons which will cover hopefully the entire course. I will be seeing you the next time. Have a nice day and bye.